Ah, yes, I can see the recording button in the corner there.
Yes, it started.
Fantastic. And so we'll be able to send it out to anybody who needs it in the future, which is great. Thank you. Okay, good. Well, we will start. Hopefully we'll have people turning up. Usually people turn up a little bit late because they're grabbing their tea and their sandwiches and everything else, but let's see how we go. Good afternoon, everybody. My name is Carl Meyer from Jayont, and I'm here just to introduce Chris Jansen from Nokia. And Chris is a product marketing manager in Nokia's IP and optical network business unit. And so he is highly experienced in the areas of IP and optical networking, which is obviously a hot topic for all of us here in the RNA community now. He's particularly looking at finance, healthcare, and education. So that he's got a great deal of experience, not only in the technologies, but in how they're used within our community, which is really exciting to hear. And yeah, he'll be at Internet 2 later on in the year. So, and hopefully maybe at TNC later as well. We may see that as well. But Chris is going to give us an overview of Nokia and of how Nokia has changed and how Nokia is moving forward in this area, and hopefully we'll have a really exciting presentation. It'll last about 40 odd minutes. We'll then have a Q&A session if anyone has any questions afterwards, and we're recording the audio, and we'll also be sharing the slides with people as and when they need those slides. So I shall hand over to Chris. Thank you very much.
Okay, thanks, Carl, and good afternoon, everyone. My name again is Chris Jansen, and I work with Nokia in the IP optical networking group. Most of my experience, by the way, is on the optical side. So as I walk through this presentation, you'll notice that's really where the emphasis is. But I do want to point out that as you see who we are, that there's a lot of strength on the IP routing side as well, which could be the topic of another discussion. But the intent here really this morning, this afternoon, was to some extent kind of reintroduce you to Nokia and who we are, and obviously most specifically in the research and education field, if you will. So by means of just an introduction, what I wanted to do was just give you a bit of a history that Nokia's had and from where we've come, because in this world of mergers and acquisitions and constant change, I know it's easy for me to forget how other various commercial entities and companies have evolved, and I'm sure for you, you may not really have been paying too close attention to where Nokia has come from. And then secondly, just sort of look at where we're at with respect to kind of the state of the art in optical transport here in 2020, and what we see as developments that have come from Bell Labs research into product development into actual product rollout, which have now found their way into the field, which will be useful, could be useful. We hope you would find useful in the various networks that you work in. And just to demonstrate that, got a couple of tidbits on some field results. And we wanted to, by the way, tee up another session like this later this year to go into more detail on those field results. And another colleague of mine would be presenting that information perhaps in a month or two. And then lastly, just a bit of an insight into what I call the way forward, really, which is where do we go from here? What's happening as we evolve beyond more and more capacity on fiber, and what sort of innovations are Nokia investing in that will help us get there? So I think to move forward here, a bit of a brief history of optical innovation. I don't want to make this a lengthy history lesson, but personally, I love history as a way to look at where we've come from and where we are today. Personally, this is a very personal timeline in the way I constructed all these logos up top. Myself, I began work in AT&T Bell Labs some 25 years ago or longer, I guess now. But I just wanted to sort of remind everyone or give you an appreciation from where we've come and how we've got to the point where in 2020 we are now Nokia. So my bias tends to be towards the U.S. side, and it tends to be towards our evolution from the old Bell system. Obviously, for those of you that have been watching this for a long time, watching Nokia, watching the industry for some years. There's a lot of other mergers and acquisitions and joint ventures involved here, including the likes of Nokia Siemens Networks, the likes of acquisition of companies like Timetra that brought in our IP capabilities. But the fundamental timeline I want you to think of with respect to optical capability is simply AT&T, Lucent Technologies, Alcatel, the French manufacturer, which then merged with Lucent to become Alcatel-Lucent, and then in 2015, I guess it was, Nokia's acquisition of Alcatel-Lucent. So much of the innovations, much of the product and the technology that I'm talking about here comes from that lineage, from the Alcatel-Lucent lineage and its evolution into Nokia. So there we are. Obviously Nokia is more deeply rooted in Europe, certainly, but we are involved in networks across the globe at this point, including all the regions that's highlighted here. So that's from where we've come. This is a little bit of chest pumping, as they say, but frankly, one of the things I've enjoyed about working with Alcatel-Lucent and now Nokia is that there's a great heritage here, and there's a lot to be proud of. There's been a lot of innovation that's resulted in a lot of different recognition from the industry. So, again, I don't want to sound too arrogant or self-congratulatory, but the truth is, our lineage involves a lot of fundamental developments, inventions that have resulted in where we are today in fiber optics. So along those lines, just a few weeks ago, I was here at this facility that this is the now Nokia Bell Labs Murray Hill facility in New Jersey. This is the original Bell Labs location. If any of you have ever been there, industrial interest aside, it's just fundamentally a historically interesting place. This is the spot where the transistor was really developed. It is the spot where a lot of research into radio, into fiber optics, into processing, into physics had originated. And if you go into the lobby of this facility, you see a lot of they have a great display setup that walks you through things like Nobel Prizes. This particular one was C.J. Davison's Nobel Prize in 1937, I think it was, for electron diffraction. And it's pretty cool. There it is, right there. There's notebooks under glass showing, various work for wave propagation. And then, to my interest, here's the actual prototype of the original transistor that Bardeen, Bredin, and Shockley put together back in the, I guess it was late 40s. Ultimately, resulted in their prize in the Nobel Prize in Physics back in '56. So if you're ever there, if you're ever in the New York area, New Jersey area, we'd love to have you stop in. Even if you just walk in the lobby to look around, it gives you a real sense of from where we've come. So, all right. So let's talk about optics a little bit. Not just Nokia, but other firms as well in this industry have long, at least for the last 10 years, been chasing the ability to put more and more information on a piece of fiber. That's not a surprise, right? The idea is how do you get more capacity out of a deployed piece of fiber? How do we utilize that fiber, that investment in a right of way in a fiber that's laid down into the ground to carry more and more information? Along about 2010 was when we saw the first 100 gigabit per second single wavelength transmission. And our evolution since then, over the past 10 years, has gone along something like the timeline that we show here. About 2013, we had introduced to market our first silicon supporting these higher data rates and coherent transmission. PSE just stands for Photonic Service Engine. And the first generation, again, 2013, got us to about 200 gig. A few years later, in 2016, we introduced the second generation of that silicon, which gave us more programmability and the ability to allow for some flexibility with respect to the actual optical span that one might be trying to operate over. And that led us to to where we're at right now today. Really, it was introduced in 2018. It was the third generation of photonic service engine, and this brought into play something called probabilistic constellation shaping, which I'll talk about more in a minute. And that got us to the point where we're looking at yet higher 200, 400 gigabits per second transmission over fiber, but also this kind of splitting with respect to flexibility, with respect to performance based on the needs of a particular span. Because the reality is, it's not necessarily the case that every optical span needs the highest potential data rate transmission. There's more to it than just that, is the point. So where are we at in 2020? A bit of the optical state of the art. A few minutes on this here. Again, what I want to stress, and I've written about this in some blogs, which I think were posted on Giant last year. But my view, there's more to this game than simply putting more capacity out on a piece of fiber. There are at least 6 different categories of requirements that we see from network operators of all types, whether they're in the research and education space, whether it's a commercial communication service provider, or just an industrial user. So again, these 6 categories, I think you could expand out into requirements that result in different technologies you see built into equipment these days. So resiliency, no kidding. For a long time, there's been the idea of just simply constructing equipment such that you've got redundant functions, you've got redundant hardware, redundant supporting systems. There's a little bit more to it than that. So when we talk about multi-fault recovery, what I'm really referring to are things like GMPLS, layer 0 restoration. I'm not going to go into some of these things in a lot of detail here, but I just want you to think about these technologies, and if you're interested, investigate some more on your own. So that's in the resiliency category. Under flexibility, the idea of being able to deploy new services, different types of services. So this gave rise in many optical platforms, the building in of layer 2 switching capabilities, of OTN switching capabilities, all of these things which really expanded optical transport networking from more than simply dense wavelength division multiplex. If we go back again in history, where DWDM started was just simply more capacity on a piece of fiber through putting or lighting up multiple colors on that piece of fiber. We're way beyond that. In fact, I bristle a little bit sometimes when people, even inside our company, think of the optical transport product line as simply DWDM. There's a lot more to this. So it sounds like a bit of a no kidding full operability with legacy and industry specific applications, but this is where the ability to do switching in different layers, different protocols, whatnot, becomes really important. So this flexibility concept is quite essential. Scalability, the third one here across the top. This is really what gets most of the attention. This is where the entire conversation around coherent detection, around things we'll talk about in a minute, things like expanding out to L-band optics, things like reconfigurable optical add drop. This is all about scaling for network growth and matching the needs of a particular network to the technology that's available. Predictability down the lower line here. There's aspects here which tie back up into my comments about flexibility. So the idea of being able to set up service level agreements and do various forms of kind of grading of types of service, perhaps preemptible service, all these sorts of things become capabilities that are essential requirements in these networks. And then the middle here, simplicity. The idea also is that as we start to build in more and more of these requirements, the systems became more complex. Managing them and operating them became more complex, and unfortunately, oftentimes happens when something becomes more complex, it becomes more costly. So what you'll see, just from Nokia, but also from other vendors, is just a lot of this development around disaggregated platforms around even software-defined networking in a lot of ways is trying to make networks or the operations of those networks more simple for you, the user, really, right? It's about trying to make them more cost-effective ultimately. And then the last category here often gets overlooked, which is just fundamentally security. So, we look at this and have been for some time um, with respect to so-called defense in depth, which is to say that security is not merely about encrypting traffic over an optical fiber. It's really about taking an approach of using a set of technologies that form not just one simple latch on the door, but a latch plus a lock plus another door in front of it. That's a third lock. This idea of defense in depth is saying that that multiple layers of protection afford the best or yield the best security. So in other words, security by design. So with respect to the optical network itself, we talk not only about encryption, but also about key management, about key quality, and then other things like how do you detect if there's been an intrusion in the network? How do you locate or isolate a particular intrusion? And provides protection against multiple threat vectors. So a bit more on that in a minute. So, that's kind of a set of requirements. Again, we can't go into all those things right now, but we want to go into a couple of them. Some of those topics are for a later day. But I like this picture because this is just taking the idea of again, as I said, we frequently want to just think about capacity and scale as the most interesting thing in optical networks. But there's really more to it than that. There's this idea of someone developed of the complexity curve, which is to say, as capacity goes up, we've tended to build more and more complex networks. So if you look at these different topics, if you will, going in the gray arrow, think about simple fixed grid optics, simple DWDM systems, those two wavelengths on a single optical fiber. It was pretty simple. It's a matter of using filters to filter out one color versus the other, or combine those two colors onto a fiber and transmit over the link. Sometime later, I guess around 2010, maybe a little earlier than that, the idea of going from intensity modulation, direct detection fiber over fiber to building coherent receivers yielded the idea of being able to immediately at least double the capacity in fiber based on using two polarizations and other things. But basically, using coherent detection allowed for a step order change in capacity, but it also became fairly complex. Coherent detection was not an easy problem to overcome, and when that became commercially viable, it was a huge step in the industry, and it allowed for a lot of these other technologies that as you go up the scale here. Coherent detection pretty much immediately, so just implied, allowed for the use of much more complicated modulation schemes, and suddenly fiber or fiber transmission started to look a whole lot like radio transmission, and conversation around using dual polarization, quadrature phase shift keying, and then multiple layers of QPSK became just very commonplace, and we see that now in the industry. So the point here is that as you go up through all these various things, complex reconfigurable optical add drop, changing the baud rate, L-band optics, and so forth, things continually get more complex. But the question is, do you really need that much complexity for every practical span that you're going to build against? And we think the answer is not always. There will always be those hero spans, and I'll show you one of those in a few minutes. But reality is there are a lot of places in the networks where you need high performance, but you want that with increasing simplicity. So this was one of the drivers for this thing called probabilistic constellation shaping. And so, PCS, as I start to use just commonly here, this is just simply the algorithm that's built into the photonic service engine. And the idea is this. It's a fairly complicated topic that I'm trying to make simple here, but in those complicated modulation schemes that I talked about, you could set up a geometric constellation as shown here on the left. And the idea is that each of those points on the constellation have equal probability based on any data stream that might be going across the link at that time. So we use each of them with each of those points in the constellation at the same probability. Well, PCS is just simply, well, not so simply, but is finally adjusting the data rate by using these low amplitude points more frequently than high amplitude points. So the constellation kind of takes the shape of this, where there's more intensity on these points towards the center, and then these other points towards the outside of the constellation tend to get used less often. So we represent that just simply in a lower frequency, if you will. So this kind of shapes the constellation in 3 dimensions to form what was a cube into a ball, right? So a more energy efficient container, we'd like to think of that. And in doing so, it increases the distance between these points at a constant signal power, and it allows us to more efficiently utilize the noise power on a particular channel. It allows us to optimize the transmission across any particular practical optical span. Another way to look at that is, again, just sort of plotting out capacity versus distance, and then thinking about these discrete quadrature amplitude modulation formats that might commonly be used. You know, be it 8, 16, 64 QAM, and so forth. And those particular modulation schemes imply a particular capacity at a certain distance across a fiber span. And by utilizing PCS, what we're effectively able to do is create a more, it's not quite infinite, but you could think of it that way, a much more granular number of modulation schemes, which is, as a result of that, pushes us out from this initial curve, this initial line, closer towards the Shannon limit. So it really just optimizes that practical span by something on the order of 25%. So we call that the 25% shaping gain, which pushes us very closer towards the Shannon limit. Of course, the Shannon limit is something of a, well, it's long been the brass ring or a goal to achieve. Again, this is all around the scalability requirement of links. So this is kind of where we are at now today. As we move forward here, what you'll see actually fairly soon from Nokia is an introduction of a new generation, or the next generation of PCS built into the Photonic Service Engine. But we've been saying with some confidence for about 3 years now that PCS, and again, it's a proprietary algorithm that's built into the Photonic Service Engine. It's what yields this shaped constellation. It's been saying again for some time that it's the only known algorithm that really approaches the Shannon limit in a practical silicon implementation. So what does one do with that? Towards the notion of flexibility, what this really, I think, yields for the network operator is just the idea of extreme programmability. So yes, you want to be able to maximize the capacity over any practical span, but how do you do that without requiring a lot of different interchangeable hardware or a lot of upfront engineering? The idea here is that PSE3, even later generations, but fundamentally probabilistic constellation shaping allows you to use a single consistent channel size, vary the capacity to match the actual performance of a practical optical span based on its signal to noise ratio, based on other impairments, and then vary that based on what might be going on over time. So it was a bit of a feedback loop here with respect to how the channel operates, but it implies a fundamental simplistic ability or more easily deployed capability for the hardware without having to go back and re-engineer things to match the span. So where has that gone, and how has that actually been demonstrated? This is going back to that original introduction of PCS was about 3.5 years ago. September 16, started as many things do in a university trial. The first demonstration of optical PCS was with T-Mobile and the Technical University of Munich, as we show here. And that kind of brought us into another public trial a few months later with Facebook, which demonstrated a 5,500 kilometer span between New York and Ireland, and operated at these at up to 32 terabits per second. So it was a record subsea spectral efficiency. So that was about not quite 3 years ago. And fast forward to today, to just fairly recently, we publicly announced this field trial, this deployment actually, as it will be, which is a deployment over the Monet and SACS concatenated subsea cable system. And to me, what's particularly interesting about this is that this total span exceeds 12,600 kilometers. That's unregenerated, so there is an amplification site at Fortaleza, Brazil, and that's where the tie-in is between the Monet cable and the South Atlantic cable system, SACS, tying Brazil over to Angola. This particular system operates at 300 gigabits per second again over that span, and it's a pretty interesting connection, because what this is allowing this network operator to do is create a pretty low latency path, ultimately between the Miami, Florida area to South Africa, actually to Johannesburg, Cape Town, South Africa. So gives them an advantage with respect to latency performance. Look for more, by the way, with respect to some of these real kind of groundbreaking, record-breaking results. And in fact, what we would like to do is walk you through some more detail on these some of these recent public systems in another webinar. But again, there's more to it than just that highest data rate. I can say that in one recent trial, we exceeded 500 gigabits per second over existing spans without re-engineering things, and there was another one that exceeded 600, as I recall. So again, stay tuned for kind of more detail on that. I want to shift gears just briefly. Again, I talked, I think I gave you a good sense of that really there's more to this overall problem than just putting more information on fiber. That's obviously a big problem. That's a center of effort for a lot of development, and that's what led us to PCS and so forth. But capacity is just one requirement. Security is, I think, increasingly important. We see that across different industries, across different types of network operators. And so that is what gave rise about 3 years or so ago to Nokia's development in key management systems. And the fundamental point I want you to think about here is just that, yes, if you've spent any time working with encryption systems on optical transport networks, you know that the idea is using AES 256 as a common standard for the encryption engine for how traffic propagating across an optical network is encrypted, and how that engine actually works, and what its encryption bit length and key strength is, or bit length, I should say. But a very important factor here, and something that often gets overlooked, is how the key that's used with that encryption engine is generated, and how that key is shared among the users, or between the ends of the optical link. And it's believed, by the way, that AES, this common standard that was developed back in, I think it was 97, AES symmetric keys are believed to be quantum safe. And what we mean by that is that in the presence of a real practical quantum computer, which is becoming increasingly a probability, a possibility, in the presence of a quantum computer, it could take a reasonable amount of time for a quantum computer to brute force the number of key permutations, the number of possible keys to break a link, if the AES key strength is, I believe it's under 128 bits. So at a realistic AES 256, the common bit strength implementation used in most encryption systems today, if you preserve that key strength at 256 bits, we could say that we believe that that the link is safe from the presence of a quantum computer. However, what happens is that if the key quality and the key distribution mechanism is used in what's shown over the right-hand side here, this concept of a distributed key management system, there's actually a reduction in key strength. This has been demonstrated by the ETSI group and by others. We can go into that in more detail at another time if you like, but the reality is that what one might think is AES 256 can actually end up being a much weaker system if the implementation is built using a distributed and asymmetric key distribution system. So we want you to think about centralized key management. We want you to think about systems that use a central key authority and a server that's located at in a safe location. And for a couple of reasons, I know in this community we tend to look at or talk about very large data transfers, and we know that the payloads are, fundamentally very critical, very sensitive. So again, centralized key management and symmetric key distribution. So how is that actually implemented? Just a real brief snapshot here. Not surprisingly, we have a product that is that key manager. Looks something like this. Fundamentally, there's a crypto module in a hardened case here that helps generate the key, and then there's some software that ultimately controls the distribution of that key out to the encryption engines that are located. The actual encryptor of the traffic is actually located on each end of any particular optical link. This has been deployed now for several years and is used by a number of network operators. One of the challenges here is for especially smaller operators, can they afford this appliance, and is that economically feasible? And as a kind of an answer to that, what we've introduced is this idea of a NetHSM secure management server. So in this case, in this implementation, the crypto module, the hardened key, let's say, random number generator is located in the Fort Knox kind of the network, and then via a secure channel, we're actually able to distribute the information about that key out to the place where, through a virtual machine, there is a connection then to the ends of the optical link. So the concept here is that one could imagine where a larger entity like the network operator buys and operates this crypto module, and then the network operator themselves buy and operate the virtual machine over on the other side here. So it allows for kind of a more economical implementation of quantum safe encryption. Whole other topic for another day, but I wanted to introduce you to that concept. So a couple things here in terms of where, or maybe it's sort of a parting thought. Where are we going from here forward? Optical networks continue to evolve. The idea of that brass ring of reaching Shannon's limit will continue. There'll be more generations of photonic service engine, but there's also a lot of interesting work that continues, as in all things in electronics, with respect to further integration, making things smaller, making things cheaper, frankly. So where are we at today with respect to density and optical componentry? I'd have to go almost. It's tempting to go back to yesterday, make a little box here that says, "What did yesterday look like?" Where we had completely discrete components that formed things like laser drivers and optical detectors and so forth. And we've had integration, obviously, into devices like the silicon DSP that we've come to call photonic service engine. And then we add to that the optical front end, right? This ACO, just meaning analog coherent optics as the front end. And we've come to use things like pluggable componentry to make things cheaper and easier for the network operator. That's kind of where we're at today. I've called this later today, meaning that you can buy digital coherent optics from some vendors, and this is somewhere where we're at. Maybe later today, not quite tomorrow. Meaning we're somewhere right on this edge of integration of the DSP into the optical front end. And you see this in some of these CFP2 type pluggables that are available from different vendors, and you'll see these. In fact, some of those components are used in different Nokia products as well. But what I'm trying to tee up or get you to think about a little bit is where we go tomorrow. Right? For a long time, there's been work done and a lot of attraction towards the idea of using silicon photonics as a way to integrate more and more of this componentry onto, ideally onto a monolithic device. That is to say, if one could, it'd be nice to have a monolithic device that would be able to perform the functions of a laser, of the passive optics, meaning think optical waveguide and combiner and other filtering components and so forth, plus all the silicon functions like the DSP that's embedded in Photonic Service Engine. If one could make such a monolithic device, it would yield a lot of enhancements with respect to integration in size and economies of scale. There's a lot of fundamental reasons that has not happened yet, including things like heat dissipation in the laser device, including the ability to create a laser in silicon. A lot of other issues like that have resulted to a point where you've got something like this, what this picture is trying to illustrate here, where there's a CMOS front end that's built on top of a silicon wafer, a dielectric component, and then you've got various types of photonic componentry, including DFB or even detector chips, devices which may be indium phosphide that are mounted on top there. So it's kind of a hybrid construction. But what I'm leading to here is just this is one of the reasons why Nokia made a recent acquisition of a company called Elenion, which is a silicon photonics company. And what you will see, I can't say much just yet, but what you will see is that this is our investment into this later today and into this tomorrow kind of view of things. So we continue to invest in trying to push the envelope and with respect to photonic componentry, and that's going to yield results with respect to the performance of our end systems. So a couple of parting thoughts or views of our equipment. What are we offering the market today? I hope some of you are familiar with the product set that we have. Two platforms I'd like you to think about or be aware of. One is a Photonic Service Interconnect. This is a low profile, highly modular, sometimes called sled-based system that allows the network operator to plug in kind of exactly what they need, largely for simple data center interconnect. And these systems use sleds that employ or PSE3 chips. And then more broadly is the 1830 PSS, which has been our flagship optical product line for quite some time now, for a number of years. And this is a modular-based system that uses a chassis and blade kind of approach. And this again uses the PSE3 in various transponder blades that get deployed in the chassis. So I just wanted to close it out with that. I hope this kind of stimulates some interest with respect to where we would fit in research and education networks. Certainly I know that the R&E space tends to be way out on that bleeding edge. So I hope that the technologies like PCS, like silicon photonics devices that you'll see coming from us, and like the quantum safe encryption componentry and key management systems that we have would spur some discussions from you folks. I'll be happy to take any questions or leave it from there.
Thank you very much, Chris. That was really interesting, and now I actually understand what the image on your blog post and everything else was all about, because we actually use that image to promote all of your articles and so forth. So that was really interesting to see how that all fits together in this kind of different way of using these techniques. And of course, as you say, R&E is very much at the bleeding edge of this stuff, with huge numbers of very, very high demanding users out there, and particularly because we're looking at relatively small numbers of enormous transfers, rather than the kind of traditional internet use of many millions of people doing relatively small amounts. So there's a completely different shift of how we do things. But I've talked enough. Has anyone in the audience got any questions that they would like to ask Chris at this stage? What I would say is that we're going to hopefully share the slides and the audio of this. So along with contact details for Chris and Helene, who is the host here. And so if you do have any questions which you don't want to share with everybody, or you want to do something privately, then be very happy to do that as well. But does anyone have anything that they wish to share at the moment? I think you've overloaded their buffers, Chris, in terms of asking in themselves and there. And so there's a lot of information there. It's really interesting stuff. So
As I said, we could go into a lot more detail on any one of those topics, and we'd like to do that in other sessions with you folks.
yeah, absolutely. No, I think the great thing about this stuff is that there's always people who want to go deeper, and there will be a lot of people around here who want to go deep. But so, any questions? I see Alexander's turned his mic off, turned his mic back on. Any questions in there? Okay, I don't think at the moment Chris, we have any questions. I'd like to take an opportunity to. Oh, actually, we have one from Janos here. Can you describe more about the quantum safe key protocol?
Well, it's not so much as that's a protocol, but the idea here, and we could certainly share a lot. It's sometimes the words come out more jumbled than I'd like, but the way I like to word this is or put this is the concept is if you look at just AES 256, that's sort of the de facto standard for encryption. Um, if the if the bit strength is maintained at 256 bits in length, this is an ETSI study demonstrated that in the presence of a practical quantum computer, it would take a phenomenally long time for that quantum computer to actually brute force the encryption, meaning actually try every potential combination of keys to successfully break the link, break the encryption. But what happens in a distributed or an asymmetric key management system is that there's actually a reduction in practical key strength, meaning that that key strength that we think is 256 bits actually winds up being 128 or 64 or something even worse. And once you get below 256 in practical key strength, say 128, the quantum computer could crack that code in something like 10 days. So suddenly, for a very sensitive data flow, whatever it might be it something as sensitive as bank transactions or whatever it might be, it suddenly becomes a real problem because if a quantum computer could crack that in 10 days, that payload is no longer safe. So the idea is maintaining key strength, and if you maintain key strength at 256 bits, then in the presence of a practical quantum computer, which has become more and more a possibility, it's highly unlikely that encryption can be broken, can be brute forced. So it's not so much that there's a protocol; it's just a matter of maintaining what we think the Advanced Encryption Standard (AES) really is. And by the way, I mean I have other materials that I can share with you on this and some papers and so forth. It's pretty interesting stuff. And the idea of sharing with you that breaking up of the hardware security manager, the HSM, from the server platform is just to try and make this solution more economically feasible for more network operators because that SMS server, it's a cost. So.
Janos, just answer a kind of supplementary there, which is talking about scalability in terms of is this an activity which can scale to hundreds or thousands of users, or
Yeah,
is there a bit of
absolutely,
a trade-off
absolutely.
there?
It's a good point. So that's exactly why this NetHSM concept is being rolled out. That SMS server itself, I think, supports something on the order of five. I think it's like five. I don't know where the number comes from. It's just short of 5,000 unique links that or rotate keys that it could be supporting for different links. And these keys sit there and rotate over time and so forth. So imagine you have imagine you only have like 30 links or something like that. Now you got to buy this system that supports actually 5,000 and is just fundamentally costly. So the idea of NetHSM is that you're able to share that cost, maybe with other users. I mean, just hypothetically, maybe a set of RNE networks buy the NetHSM system. They physically put that crypto module in a secure location and via a secure channel distribute out to all the all the users in the consortia.
That's very interesting, actually. I do know that there are a variety of very, very intelligent people in our organizations looking at that kind of activity at the moment with HSM. So it's a definitely emerging trend of area. And like I say, if you have, white papers or whatever that you'd like to share links to, then I'd be very happy to distribute those to the community, because we are a complete sponge when it comes to that kind of information. So yeah,
I can
absolutely.
do that, Carl. I can send that to you, as well as, by the way, this presentation from today.
Fantastic. No, that'll be great. Okay, so okay, Janos, if you have any other questions, what I'll do is I'll drop you Chris's email address so that the two of you can discuss at great length those kind of things, which will be really useful. But what I would now to do is probably wrap up so people can have a bit of lunch. And I would say to Chris, thank you very much and you can go and have some breakfast, because I don't know if you know, but Chris is actually over in the East Coast at the moment. So this is sort of 8 o'clock in the morning for him coming up. So he's got up early to talk to us. And I'd like to extend our grateful thanks to him for this. And thank you all for attending. And I look forward to the next session. So thank you very much, Chris.
Thanks, Carl. Thanks, everyone, for joining.